This is an asteroid. It's a rock. It's floating in space, left over from the birth of our solar system. And there are millions of them. Most are just rocks. But some of them are worth more than the entire global economy. You've probably seen the headlines. One asteroid, like 16 Psyche, having a value of $10,000 quadrillion. That number is kind of meaningless. It's based on taking all the metal in that asteroid and dumping it on Earth, which would crash the market instantly. But the real value of these rocks isn't about making everyone on Earth rich. It's about building an entirely new economy off of Earth. It's the next great resource rush. And the prize isn't just metal, it's water. So what are these things actually made of? Asteroids aren't all the same. Scientists sort them into three main types. Asteroids are rocky, metallic, or icy bodies with no atmosphere and are broadly classified into C-type, carbonaceous, M-type, metallic, or S-type, silicaceous. Then you have S-type, for stony. These are made of silicates and some nickel iron. And the rarest, most famous ones, M-type, for metallic. These are basically giant flying chunks of iron, nickel, and precious metals like platinum and gold. About 75% of the ones we know are C-type. The C stands for carbonaceous. On Earth, when the planet was a molten ball, all those heavy, valuable metals sank to the core, forever out of our reach. But M-type asteroids are thought to be the cause of early planets that were smashed apart. All that metal is just sitting on the surface. But here's the twist. While the M-types get all the press, the real money target for the next 100 years, it's the boring, dirty C-type asteroids, and it's all because of the water. These are dark, crumbly rocks, rich in carbon, organic compounds, and water, locked away as ice or hydrated minerals. Think of them as giant, dirty, floating snowballs. To understand why water is the most valuable resource in space, you need to understand one thing: the tyranny of the rocket equation. Reusable rockets have made it cheaper to get to low Earth orbit, or LEO. But getting from LEO to the Moon, or Mars, or anywhere else, that's the real bottleneck. Every bottle of water you send to the space station costs thousands of dollars. For an estimate, a liter of water costs around $20,000. But what if the water was already in space? C-type asteroids are loaded with it. You could fly a mining robot to one, heat up the soil and capture the water vapor. And here's the kicker. You don't just drink it, you run an electric current through it, electrolysis, and split it into hydrogen and oxygen. That is, literally, the most powerful chemical rocket fuel we have. Asteroid mining isn't about bringing gold bars to Earth. It's about creating an orbital economy. Gas stations in space, where missions can top off their tanks. So, if this is such a great idea, why aren't we all driving space yachts fueled by asteroid water? Water for radiation shielding. Water for astronauts. Iron and nickel from M-types, 3D printed into new satellites in orbit. This is how you build a real, lasting presence in space. Problem 1. Distance. Even the near-Earth asteroids aren't that near. A round-trip mission can take years. NASA's OSIRIS-REx mission? It launched in 2016. It reached the asteroid Bennu in 2018. It collected its sample in 2020, and it finally got that sample back to Earth in 2023. A 7-year journey. Problem 2. The environment. These aren't like the asteroids in Star Wars. They're often not solid rocks. They're rubble piles, loose collections of gravel and dust, spinning in space. How do you land on that? How do you anchor yourself in zero gravity to drill? Dust is electrostatically charged, so it sticks to everything. And all of this has to be done by robots, with a 20-minute communication lag in a vacuum, with temperatures swinging hundreds of degrees. And problem 3, the cost. We're talking billions of dollars for a single unproven mission. The first wave of asteroid mining companies all quietly failed. The money ran out before the technology was ready. So assuming you get there and you don't run out of money, how do you actually mine? For a small asteroid, you might not mine it at all. The simplest idea is bag and grab. You find a small rock, and a robotic ship just captures it. Then you can tow the whole thing somewhere useful, like an orbit around the moon, to be processed. For a bigger target, you need to land and dig. This is what NASA's OSIRIS-REx and JAXA's Hayabusa 2 missions basically did, just on a tiny scale. Hayabusa 2 fired a projectile. OSIRIS-REx used a puff of nitrogen gas. Both collected just a few grams. A commercial mine would need to scale this up by a factor of 1,000,000. For water, one popular idea is optical mining. You build a giant tent over a patch of icy soil. Then, you use mirrors to focus sunlight. The heat turns the ice into water vapor, which you capture and condense in a tank. No heavy moving parts, just sunlight. And maybe the most futuristic idea, robot swarms. Instead of one giant, complex, expensive lander, you send thousands of small, cheap, autonomous bots. If a few hundred fail, who cares? The swarm keeps working. Okay, so we have the what and the how. But there's one more, very human question. Who's allowed to? In 1967, the world signed the Outer Space Treaty. It says very clearly that no nation can claim sovereignty over a celestial body. You can't plant a flag on the moon and call it yours. But the treaty is old. It says you can't own the rock. But does it say you can't own the stuff you dig out of it? Most people point to international law on Earth, like the law of the sea. You can't own the ocean, but you can own the fish you catch there. In 2015, the US government forced the issue. It passed a law that explicitly gives American companies the right to possess, own, transport, use, and sell any resources they get. Since then, other countries like Luxembourg, Japan, and the UAE have passed similar laws. They're creating safe havens for this new industry. But it's still a legal gray zone. What happens when two companies from two countries show up at the same asteroid? We don't know. It's the Wild West, waiting for its first standoff. Despite the hurdles, a new generation of companies is giving it a shot. But the real progress right now isn't coming from startups. It's coming from science. The most important asteroid mining missions so far have been NASA's OSIRIS-REx and JAXA's Hayabusa 2. Their goal wasn't profit. It was to understand the origins of our solar system. And what they found is revolutionary. Both missions successfully grabbed samples from C-type asteroids and found them loaded with water and complex organic molecules. Hayabusa 2's sample even contained amino acids, the building blocks of life. These missions proved two things. 1. The raw materials for life and our oceans were probably delivered to Earth by asteroids. And 2. The stuff is there and we can grab it. They built the map for the miners to follow. So what does this all mean for us, back on Earth? Is asteroid mining going to make platinum cheap? Maybe, eventually. But that's not the point. The first resources mined in space will almost certainly stay in space. Because the real prize is breaking the tyranny of the rocket equation. It's about building a self-sustaining infrastructure in our own backyard. A 3-step plan. 1. Mine water from asteroid. 2. Create rocket fuel in orbit. 3. Build solar panels, satellites, habitats in space. When you don't have to launch every single screw and gallon of water from Earth's gravity well, the cost of everything in space plummets. Building giant solar power stations, moon bases, even missions to Mars, it all becomes, suddenly, possible. The first space billionaires won't be the ones who bring $1 trillion rock to Earth. They'll be the ones who build the pickaxes and shovels, the refueling stations, that let the rest of us get there. It's a fundamental shift, from a place we visit, to a place we live.